TypeScript's type system is weak. TypeScript is supposed to improve the quality of your code, make your developers more productive, make your code more maintainable and approachable, make your customers trust you more, and over time cost you less. In this video, I'll go through 5 weaknesses of TypeScript's type system and explain each while linking to a deep dive video so that you can go explore on your own. Okay, so let's talk about null safety. And with null safety, we're talking about the dreaded null pointer exception, which occurs at runtime. So in TypeScript, this works, but the developer has to remember that a type can be nullable, for example, or that a scenario in which you're accessing something can result in a null case. So for example, in one of my videos, I go through the example of accessing a DOM element on the page. So long as the developer remembers to specify that the type is of HTML element or null, then it will work. But without that, it will not. You will run into the same runtime errors in production, where you're accessing an element on the page, it's not there, the developer's forgotten to specify that it's nullable, the application compiles, you get this false sense of trust, and then there you are, you're in a production scenario and you have a null pointer exception, or you have in the case of JavaScript, you have a runtime exception. So this fails to deliver on the TypeScript promise in all the areas. The code quality suffers, your trust with customer suffers as they see things in runtime at the runtime of the web application broken. Your developers have to go back and reactively fix the problem, which is not ideal. It's going to cost you in their productivity as they're sidetracked, and of course it's going to cost you time and budget. The nice thing is that other next generation web development languages deliver on this promise out of the box. And if you want to see a deep dive video on that, I'm going to link it right here. Let's talk about safe array access. And here we're talking about array bounds checking, where you're at runtime, you try to access an element in an array and it's out of bounds. So this is what we're calling unsafe array access. This is a problem which TypeScript does not solve, and it fails to deliver again on the promise of code quality, customer trust as they see these things pop up in production, developer productivity as they react to the problem, and of course time and budget. But safe array access comes out of the box in other next generation web dev languages. And if you want to see an example of going through this problem and showing a counterexample in a next-gen web dev language, then check out my video, which I'll link here. All right, let's talk about the problem of implicit conversion. So this is a very pervasive problem with JavaScript, and it results in unexpected outputs, like say you're adding 5 and 3 together, and instead of 5 the number, you're adding 5 the string. And so instead of getting the expected answer like 8, you get something like 53. And that does not get caught at the source of the implicit conversion. It gets propagated down the call stack, making it hard for the developer to debug and find the source of the error. So this is again a failure of TypeScript to deliver on many promises. Code quality, as the developer is can't find errors at the source of their true problem. Customer trust, as you take time to try to debug these complex issues and they see these things in production. Your developers are going to be sidetracked when it comes to the feature they're working on, but they have to go back and debug this hard to debug bug. And the maintainability of your code will suffer too, as the application compiles, but again, the trust is not there with these runtime issues. And so this is a problem that other languages solve and just deliver right out of the box. The problem of implicit conversion, it's just disallowed. And if you want to see an example of this with TypeScript and how it's solved in another language, I'll link to the video right here. Next, let's talk about exhaustive type checking. This is when all scenarios for a given type have been coded for. And without this, you're going to run into runtime errors where there's a valid pathway in the code. It just hasn't been coded for yet. And it's just unhandled. So you're going to want to have exhaustive type checking because you want your developers to be proactive in their engagement with their code and not reactive. And this is where TypeScript fails to deliver on the promise. It doesn't increase, for example, developer productivity because they get distracted again. Once an issue happens in production at runtime, they're working on a feature, but they got to go back and debug this problem. Your code quality obviously suffers in that particular scenario. Your time and budget gets wasted, and as they spin cycles on going back and being distracted from current features, and the customer trust as they see scenarios that ought to be handled in the modern web not being handled in your UI. So again, next generation web development languages have exhaustive type checking, and it comes like that out of the box. That means the code won't compile unless all the snares for that given type have been coded for. May not be right, but it has to be coded for by the developer, which encourages a proactive thinking on behalf of the developer. So if you want to see an example in TypeScript, how it fails to do this and how other next-gen web dev languages deliver, I'll link to the video right here. Lastly, let's talk about structural typing. This is when you have two types, they have the same shape, but you can input them, for example, into the same function. And how strange is that? In finance, this could be disastrous if you have one structure that represents funds and another that represents debt, and they have overlap in their type shape. In TypeScript, there is no nominal distinction. However, in other languages, there is. And this is a failure of TypeScript, again, to deliver on a bunch of promises. Customer trust. You can imagine how disastrous it would be for them to see their funds represented as debt or debt as funds and so on. Developer productivity, as again, they react to the problem instead of proactively engaging. The quality of the code suffers, and especially as you have TypeScript promising safety and you begin to trust it, but then a semantic loophole comes up, like the one I just described. So it's going to cost you time and budget and maintainability as people try to scrutinize what's wrong with compiled code that should work. So, I mean, other next-gen development languages do not have structural typing. They have the types are nominal. There is distinction between the names of types, even if they have the same shape. So you can't, for example, plug two types with the same shape into a function and have it compile. It just won't work, even if they have overlap in their shape. So if you want to see a deep dive on this with TypeScript and see a counterexample in a next-gen web dev language, then I'll link to the video right here. If you want to see more experimentation with next-gen web dev techniques and languages, be sure to subscribe to my mailing list. Subscribers will get timely notifications about my latest videos, as well as access to my personal email. Thanks again. Bye now.